Hello and welcome to another week of physics. I hope you're all well and you've had a lovely weekend. So today we are looking at resistance, and some of this will be GCSE level bits, so I'm hoping you vaguely remember. Don't worry, I will tell you everything. I won't expect you to remember, but hopefully some of it is vaguely familiar to you. So if you title and date, it's obviously not the 17th of December today, so whatever day it is when you're seeing this, and then let's crack on. So first bit is the resistance is how much energy it takes for electrons to flow through something. Now that's the kind of colloquial definition. I haven't seen an exam question that says what is resistance, but if I do come across one, I will obviously make sure you have an official definition that you can answer with. But that's the way I describe it because it's really good for you to be able to understand it in terms of electrons. So how much energy it takes for electrons to flow through. High resistance slows them down and takes a lot of energy, whereas low resistance allows them to travel fast, not taking much energy. And it is measured in ohms, which comes after Georges-Simon Ohm, who's a French scientist who came up with Ohm's law as well. Yes, so lovely, pop that down, let's crack on. So 1 ohm. Please notice an ohm is a unit, which means when we define an ohm, if you're asked in an exam question, you should only use units to define it as well. So 1 ohm is defined as the resistance of a component when a potential difference of 1 volt is produced per ampere of current. As in, if you have 1 amp of current flowing through it, so a certain number of electrons flowing through, you will have 1 volt of potential difference or potential energy being used in it. So 1 ohm equals 1 volt per amp. Ohm's law, and you do need to know the written Ohm's law for A-level as opposed to GCSE where you just had the equation. For a metallic conductor kept at constant temperature, the current in the wire is directly proportional to the potential difference across its ends. Now, one of the key things that people always forget is this bit, kept at constant temperature. And we will go into why that is important in a moment. Okay, so you've seen this before in GCSE. Ohm's law in equation form, resistance is V over I, or we used to write V equals IR, if you remember. And there you go, that's Georges-Simon Ohm that we were previously talking about. Okay, so the next bit we're just briefly going to, in fact, no, I'm skipping. Resistance is directly proportional to the length of the wire. If you double the length, you double the resistance. Resistance is also inversely proportional to the cross-sectional area of the wire. The thicker the wire, the less resistance. So the way you can think about this is in terms of corridors at school. If you have a long corridor, it's going to take twice as much energy as a short corridor to get down. That's fairly logical. If you have a wide corridor, you will be able to travel much faster with all your classmates than you would if you were down a narrow corridor where you're all bunched together. Okay, and the last bit we're going to look at is temperature and resistance. So I'm actually going to show you this on Caboodle, because normally if we were in class you'd be taking textbook notes. I'll talk you through it, then you can either go to your own Caboodle or you can screenshot this and take notes from it, and then we'll all join together on Zoom to do the summary questions from this page. So what we're looking at today, I cannot work Caboodle on here, is temperature and resistance. So I want you to have a little look at this, oh my gosh, I'm so bad at this, setup here. On the left-hand side, you have a circuit diagram. You have a cell, which is providing our energy, a switch, S, an ammeter to measure the current, and your component you're looking at is actually a bundle of wire. So they switched on the circuit, and at first, if you have a look at the graph, they were measuring current against time. First, you actually had a very high current. You had 3 amps of current flowing. Then, as time went on, the current decreased until it stabilized out at about 4 seconds of 1 amp of current. Now, knowing that 1.5 volts was provided by the cell, they could work out the resistance at the different points. So if you look at 0 seconds, they've worked out the resistance by saying R is V over I, so 1.5 divided by 3. So the resistance of the circuit initially was 0.5 ohms. However, you can see resistance increased. By the time it got to 4 seconds, it was 1.5 volts, that stayed the same, divided by 1 amp of current, giving you 1.5 ohms of resistance. So you can see it's got 3 times higher in the 4 seconds that circuit was switched on for. Now the reason that has happened is that wire will get hot. And as the temperature of that wire increases, its resistance also increases. Now I know there are things like thermistors, which we will look at later on, where the opposite is true. However, unless you are looking at a thermistor, everything else pretty much, as it gets hotter, the resistance increases. So that's just our general rule. So if we just scroll down, the current in the circuit changes because the temperature of the wire increases over time as a result of heating caused by the current. As the wire gets hotter, its resistance increases. So here we have 2 wires. On the left-hand side, you have a cool wire, and on the right-hand side, you have a warm wire. On the left, in the cool wire, you can see that those positive ions, those red blobs with the little positive signs in, are not really moving very much. Of course, they are vibrating, but for the purposes of this diagram, because they're cool, they're not vibrating very much. That means the free electrons that are flowing through the wire and are acting as our electric current can go through without really any interference. On the right-hand side, however, when you have increased the temperature, the ions start vibrating more, and so they get in the way a little bit more. And so the electrons that are trying to get through collide with them and have to move out of the way, and it just slows them down generally. So the current ends up decreasing because of its resistance has got higher. Now the way I imagine it is trying to carry a tray of drinks through a party when everyone is playing musical statues. On the left-hand side, everyone is being a statue. And fine, you have to kind of dodge around them, but you can get through fairly quickly. On the right-hand side, when the temperature has increased, everyone's in that dancing place of musical statues. And so actually, you have to avoid people's arms swinging about wildly, crazy hip movements. If you're, a dad dancer, that's fine. And so actually, trying to carry that tray of drinks through the party, if you were the electron in this analogy, you would be much slower. So that's my kind of explanation. So here, this is what the book says. When the temperature of a wire increases, the positive ions inside the wire have more internal energy and vibrate with greater amplitude about their mean positions. The frequency of the collisions between the charge carriers, free electrons in the metal, and the positive ions increases, and so the charge carriers do more work. In other words, transfer more energy as they travel through the wire. Other factors as well as temperature affect resistance or the length of wire, and these are discussed in topic 9.7, resistance and resistivity. So that's with the length and the area bit. I gave you a preview there. So please take notes on this. You will want this diagram, you will want bits of the explanation. And then join me on Zoom and we'll do the summary questions. All right, thanks everyone.